Hi everyone, I'm Billy and I'm a Senior Solutions Engineer here at Grafana Labs. Today I'd like to share with you how I'm using Grafana and Loki to improve my astrophotography and remove those annoying star trails we see in our images. If you've ever taken images of the night sky before, you will know that after taking long exposures of more than 5 or 10 seconds, your stars will start to trail. However, if you'd like to capture stunning images like this one, you also need multiple or very long exposures. Now, how do we do this? In this presentation, I'm going to talk a little bit about the problem of star trails and the techniques we can use to work around the problem of the Earth's rotation. To do this, we also need to understand how to navigate our sky and find and track objects reliably. As with most things, once you solve your first set of challenges, new ones are introduced. I'll also talk about a program called PhD2 and how it's used to improve our tracking and where Grafana and Loki can be used to improve on PhD2. And finally, at the end I have a little bonus video for you with what's possible when using these techniques. You can contact me via email or LinkedIn afterwards if you have any questions or just want to talk about today's presentation. So you've just bought your first camera, a tripod, a nice lens, and now you want to take your first images of the night sky. You set your shutter speed to 30 seconds to capture some good detail, and the first thing you see is trailing stars. And these trailing stars can be really annoying and they basically ruin your photo. You might elect to shorten your exposure time to say 2 or 3 seconds, but then you lose out on capturing those fine details. Especially with nebulas, they require many hours worth of combined exposures, and taking thousands of 3-second exposures will blow up the storage of your memory card or hard drive and will take many hours to process. What if there was a way to take multiple minutes worth of exposure in one take, but without any trailing stars to ruin it? How would we do it? Well, before I answer that question, let's have a quick discussion on how to locate any object in the night sky and how we use these coordinates to track them accurately over a long period of time. Much like how we use longitude and latitude to locate streets and buildings on maps, our sky is divided into two measurements called right ascension and declination. Declination is easy. It is the amount of degrees up or down from the equator. If you live in the northern hemisphere, positive 45 degrees means the object is about halfway up in the sky. Right ascension, on the other hand, is how many hours of rotation it needs to take for the object to appear right in front of you, relative to the vernal equinox, which is in March. It's a little tricky to explain, but imagine our star is at 3 hours of right ascension. This means that the object was 3 hours worth of rotation away from what was directly in front of you on March 21st. By using this coordinate system, we can now describe the position of every object in the night sky, be that a star, a galaxy, a nebula, even the moon or the sun. We can also calculate the exact path it'll track across the night sky as the Earth rotates, and we can use this exact location to our advantage, explained later on. It also means now you have an idea of popular objects in the night sky and roughly where they are located. The black hole in the middle of our galaxy, our closest neighbor, or even the second brightest star in the northern hemisphere, Vega. Reading the coordinates, you can tell whether it is visible in the northern or southern hemisphere and roughly how long you'd need to wait for the Earth's rotation to bring the object to your visible view. But how do we use this to improve our imaging? Well, while we have our main imaging camera or telescope, we can add a second lens or smaller telescope and designate it the task of guiding the main camera. The smaller camera can take continuous images of the stars, track its relative movement, and counter-rotate your tripod or motorized mount. And basically this keeps the sky still for minutes or tens of minutes at a time. Let me explain. Imagine we have a self-driving car. The car's aim is to stay in the middle of its lane, roughly on the green line. To do this, it will constantly use radar to scan the road, read its relative position and how far away it is from the ideal position, the green line. It'll make subtle movements to steer the car closer to the green line and start the process again, over and over, scanning the road, adjusting the car to stay as close as possible to the main target. It'll move it a little bit left, a little bit right, a little bit left and right, and so it goes. In astrophotography, we do the same. However, instead of scanning the road, we're scanning a star more or less in the same location of what we are taking a photo of. Our guide camera, shown in red here, will loop every 2 seconds, take a quick image and send us to a program called PhD2, commonly used among many astrophotographers. PhD2 will know the position of the star in the image, but it will also know where the star really should be and tell your tracking mount how to move to correct itself. A little to the left, a bit to the right, maybe a bit up or down. You can see these red and blue lines in the graph at the top. These are calculations PhD2 constantly makes to calculate how far you have drifted away from the correct location and how big these corrections should be. The flatter the graph, the smaller the corrections were, and you're really trying to aim for a graph that's as flat as possible. No large spikes or anything like that. These corrections are constantly made in declination and right ascension. This loop runs constantly every 1 or 2 seconds for the whole night, constantly sending small little corrective pulses to point your camera at the right place in the night sky so that it appears as if the sky is not moving at all. As the Earth rotates, it gives the appearance of the night sky moving across your field of view. This is what gives you star trails, really. But if you can counter that rotation every second to your camera or telescope, it will appear as if the sky is not moving. Now you can take exposures lasting many minutes without any blurring at all. And if you get this right, you'll have nice round stars with long exposures. If you look closely, you'll even see faint stars in the background, which would not have been possible if this was a 2-second exposure. So what does this have to do with Grafana, and how can Loki help us? Well, here is a recording I made of the app that I use to take my images at night. You can see a guide star selected in the middle by the green intersecting lines. And on the bottom you can see the right ascension and declination of the star. By constantly measuring its location and comparing it to what its real location should be, we can calculate our drift and send those corrective pulses down into our motorized mount and keep the star in the sky still. You see that number there at the bottom where it says total 0.96, 0.98. That's in arc seconds, which at my focal length is around 2.5 pixels. That's 2.5 pixels of the camera that the star is moving about, which is super accurate. This really prevents any blurring from happening at all. However, this still presents us with a few challenges. The chart you saw on the previous screen, the red and blue lines, really only shows you the guiding accuracy of the past 1 or 2 minutes. You can't really scroll back to earlier in the night or even see long-term trends. You also can't really see anything if you leave this outside and go to bed. There's no way to go back and see what happened at 2 a.m. while you were sleeping. Luckily to our rescue are guide logs. PhD2, the program you saw in the previous video, keeps a running log of every 1 or 2 seconds and the various measurements and corrections taken. And at Grafana, we have Loki. Loki works with logs. So what if we try and combine the two? Well, yes. Here is an example of one of the logs. Looks a bit like a CSV actually, with various columns and numbers. The most problematic column is the second column, which is relative seconds from the start of the measurement taken, rather than actual timestamps. Unfortunately with Loki, we need actual real timestamps and not relative time to work. So our first step will be to fix this. I wrote a Python program that can read these guide logs, read the relative time offsets, and recalculate the exact timestamp into a format that Loki will understand. I also don't need all of the fields in the original log, so I can just pick the few that I'm interested in. These I push into Loki via the REST API, and now I have something to work with in Grafana. Inside Grafana, I'm now able to use the Loki query language and the pattern parser to essentially read each field of my CSV output and turn those into various columns that I can use to create metrics and graphs from. You can see columns dec and RA and even SNR for signal to noise, which is in yellow on the graph above. Really, you're looking for a graph that looks pretty stable actually, not this jumping up and down you can see on the right. Let's go back to my imaging application. This is a 2-minute exposure, and unlike the previous video where we were looking at the guide star and tracking graph, we're in the main application where we look at the output image that we're trying to capture. We're still waiting for the capture to finish, but while we wait, we can see at the top of the screen the output of PHD2 and the corrective actions in red and blue for declination and right ascension. Guiding seems to be good at less than 0.9 arcseconds or about 2.2 pixels on the camera. Let's give it a few seconds to finish. We'll wait for the countdown timer to reach 0 and wait for the image to load up. Wow, did you look at that? This is M51, the Whirlpool Galaxy. We can zoom around a bit and see the incredible detail here. Remember, this is just one image of 2 minutes worth of exposure. Our stars are nice and round, so no trailing, and because of this we can capture all this incredible detail. You can even see some dust lanes in there. Honestly, actually, this never really gets old. You can even see a satellite trail in the bottom right corner of the image. And that's not really a problem, we can process this out later. Back in Grafana, we can now load up all of our guide logs in Loki and have a much deeper look. In this video, I loaded 2 nights worth of logs, one for the 26th of April and another for the 27th. We'll start with the 26th and zoom in a bit. There's a couple of spikes in the beginning, which is fine. This is just part of the setup procedure. Then what looks like nice flat graphs in the middle from around 9:30 till about 3 a.m. And from there, just massive spikes in the yellow and red colors. The flat and uninteresting bit in the middle is what you want to see. You want to see red and blue remain within the gray marked area. You want to see stable signal to noise in yellow, and these will also translate into really good images. However, the bit on the right is a real mess. Lots of jumping up and down, huge spikes way beyond the safe zone of 2 arcseconds. Without having to look at the image, I can tell you these are blurry and unusable. In this case, we actually had some light cloud cover moving from 3 a.m. Moving on to the 27th, this night was a complete washout. Actually, there's some good data between 11 and 12 at night, but after 12 you can see tons of gaps in the data, not even spikes at all. Unlike the previous graph where we had light cloud cover, on this night there was complete clouds from 12 a.m. and it was unable to track at all. All these images are ruined, and in fact I ended up just deleting everything for this night. So to summarize the benefits of using Grafana and Loki, I'm now able to view the whole night's worth of imaging data and able to determine long-term trends like cloud cover moving in or anything else that would ruin the photos. I'm also able to go back to any night and compare with another night, and this all adds up to saving me tons of time trying to process images that are unusable. I think this is a win in my books. And one more thing. I'd like to show you a little video of what's possible after a few months of practicing and using the various techniques discussed to improve your nighttime imaging. Thank you for watching, and I'll see you soon. Enjoy!
Hey everybody, how are you doing? Thanks for watching the video. I hope you enjoyed that. I have my colleague Ward Becker to help me out as well to read some of the Slido questions. So Ward, over to you.
Yeah, hey folks, great to meet you. Yeah, so there's a bunch of questions actually in Slido, so thanks so much for that. And yeah, do we still need to use James Webb, Willie, the
Unfortunately,
telescope?
yes. Unfortunately, yes, you do. James Webb is just a little bit more expensive and better quality than what I can run at home, and it can do real scientific experiments that I can't do. So yeah,
Well, it already looked really awesome, so really great to see.
thank
Um,
you.
there's a bunch of video questions, of course. Let me pick one. How do you deal with satellites in the image? That's a
Uh,
good one.
yeah, and I wish I could wish them away, tell them not to cross my path, but unfortunately, it's a reality of astrophotography, and more so. However, it's actually not really a problem. If you take many images, say 100 or so, the software program that you use to stack these images is actually pretty clever. So it can see that in one of the 100 there was a line that you saw in the video. There was a line which is not in the other 99 images. So the software is just clever and just removes all of that. So it's as if there wasn't a satellite trail at all, but it does mean you need to take about, I don't know, 50 or 100 images for this effect to work. So yeah, it's not really an issue.
Cool. And another question: what are the benefits of using Grafana Loki to display PHD2 graphs or using a PhD viewer? All kinds of very nice acronyms. You probably know what they're talking about.
Yeah, so the graphs you saw in the video in Loki, so those are PhD2. So PhD2 is the program that records, the corrective actions, and then I show the graphs in Grafana. We actually also get a dedicated program called PhD2 Viewer, and where you can upload the log file of the night into the PhD2 Viewer, which is a Windows application. And then you can do similar things like Grafana. You can scroll back forwards and backwards during the night. You can view the night session. Uh, the downsides of PhD2 Viewer, the application, is that A, it's an application you have to install on your machine, and B, it's hard for me to share with you because you would have to install the application. I would have to send you the file that you upload, and it's hard to like look at the same graph. Where if you do it in Grafana, the benefits of Grafana is it's all web based. I can give you a URL and we can look at the same data on our browser. So it just makes it a little bit easier. But PHD2 Viewer is definitely an easy way to start to look at your graphs.
Cool. All right. Well, some viewer, and I think it actually got multiple likes, commented out that there were Georgia. How do you pronounce that in English?
Gorgeous.
Gorgeous. Thank you. Not a native
Fantastic
English speaker.
photos. Yeah, thank you so much. Thank you so
Yeah,
much, Eds.
that's really nice. And talking about those colors, are those images using kind of natural color, or is there like post processing needed to get those really bright colors out of those star systems?
Yeah, it's a little bit artistic effect. So of course you can't see hydrogen and oxygen or sulfur. If you could, you would see it in the air around you. So what we do is we use special filters to extract just the hydrogen signal out of the photo. Same for oxygen and sulfur. And then we pick a color and represent, well, I think hydrogen is going to be red and oxygen is going to be blue and sulfur is going to be yellow, or anyway combination. And it's really up to you how much red and blue you mix to make up the image. So it's a little bit of an artistic effect. The data is real, but you decide like to which degree you want to represent each like data signal. But the image you saw, the last image you saw in the video, the monkey nebula, that was represented using the Hubble palette. So it's actually a fairly common palette or way to represent. So if you've ever seen Hubble photos, like, oh, well, I've seen that, that gold blue kind of color. Yeah, that's the Hubble palette. So I tried to process the photo, using the same Hubble palette formulas just to give it the same effect.
Awesome, awesome. And what color does dark matter has in your photographs? Did you?
Oh,
Did,
it's a dark color, yeah. So everything. No, I don't know. I don't have a filter for dark matter. I wish to.
yeah, I just saw a video today on dark matter. That's supposed to be a lot of that, but we cannot take pictures of that, unfortunately.
Oh yeah.
Um, anyway, a little bit more in my ballpark. Was any consideration given for using metrics to record all the data versus logs?
Yeah. I actually initially started the project using metrics instead of logs to try and
Mm,
represent the data, but I soon ran into a couple of issues. The first one is, again, that program PhD2 that records all of the corrective actions.
right.
Although it records to a log file, the file is actually only written at the end of the night. It's only then written to disk.
Uh,
So it's hard to, as the night runs, hard to collect the metrics because the file isn't there at all. Only on, like, 12 hours later when you end your imaging session. So which then means, like, if I do process the file and extract the metrics out, some of those metrics are now 12 hours old, and Prometheus doesn't like data that's very, very old.
right.
So for that reason, I switched to using Loki, because Loki by default, at least the one that I used, I could go back 3-4 days and upload log files that's like 3 days old. So as long as I upload within 3 days an imaging session, then yeah, that's pretty easy. So I just switched to Loki for that reason mainly.
Okay, cool. And you can always write from Loki. You can always create Prometheus metrics if you still want that, using
Yeah.
recording rules, obviously. Yeah.
I'm thinking of adding something like that. Yeah.
Yeah, so I think you basically answered the next question that I see here is, can I use Loki that I run at home to record and display this data?
Yeah, absolutely. You can. I happen to use Grafana Cloud logs for that, free tier, no problem. But there's no special feature out of Grafana Cloud logs that I've been using. It's just, hey, it's free. So if you want to run Loki at home and parse those PhD2 files and send them to a Loki that you run yourself, perfect. Yeah, it's not going to matter. You don't need an enterprise version of Loki.
Great, awesome. Um, and somebody asked that in the video, next to the graphs, there were some contextual data as well, like exposure lengths, target types. So where did you actually get this data from? How do you make that appear in next to the graphs?
Yeah. So actually, again, PhD2 program, it records a lot of information. So what I showed in the video was just the corrective actions, but between all of those lines, it actually records a bunch of other information. So like when it'll tell you, like, okay, I'm starting a photo. It's going to be 180 seconds. I'm pointing at M51, or I'm pointing at some nebula. So all of that textual data is also mixed in between the corrective data, so the
Hmm.
metrics data. So the PhD Python program I wrote is corrects for the timestamps, but it also extracts out all of this text data, and then I just display it side by side to the visual graph. So it's actually the same file. I just like split it up into different
Right.
log streams.
Yeah, basically different uses of different ways to use the same data or from the same data source.
Yeah.
Exactly. Yeah, that makes a lot of sense. All right, and we already talked about satellites, but um, other than like clouds, what else could cause the graph to show erratic behavior?
Yeah, I think there's two things that would cause a blurry image. So star trails, essentially. The first one is something external. So it is clouds. It's perhaps an unstable atmosphere that could
Mm,
cause some blurriness to your photo. And the second one is something more physical. So wind. So it's surprising if the wind blows strong enough where I put my telescope. It actually just very slightly, but it very slightly wobbles the telescope. You can't see it, but it's enough for the data to be blurry. So that's one. Is also if I walk around the telescope,
right.
especially if I put it on the concrete slabs. If I walk around the telescope, that's just enough to blur the telescope or rattle the telescope. So again, it's a no-go zone. So once it's all set up, you're in the house. You do not go outside. No touching, no looking. Just stay inside and do it over the Wi-Fi.
No big parties in the house during the telescope runs.
Oh
Yeah,
no,
awesome.
not for
And
sure.
do you live somewhere where you have especially dark skies, or what's the situation there?
So you can do astrophotography even if you live in a city. You just get special filters again that isolates those really tight narrow bands of hydrogen, oxygen, and sulfur. So it's really
Mhm.
no problem if you do live in a city. I live not in a city. I live in a town, so about 100,000 people, and live on the edge of town. Skies, night sky is classified in the Bortle range, so Bortle 1 to Bortle 9. Portal 9 is if you live in London or Paris, so really, really bright sky dome. And
Yeah.
Portal 1 is if in the Nevada desert. And then, the range in between. So as a town, of 100,000 people, you would be Portal 5, Portal 6, somewhere in the middle. And that's where I am. So I kind of have half dark skies, not completely dark, but enough that, it makes my imaging a lot easier than from city lights. But you can still do it from city lights.
Cool. And so the last question, I think we're almost up for time. What's your? Are you going to buy a bigger telescope in the future?
My fiance is watching. Always. No, you don't buy a bigger telescope. You watch. Sorry, you buy a different telescope.
A different telescope. Okay,
Yes,
good.
a wide angle or a solar one for taking images of the sun or something. So it's never bigger. It's just for a different reason.
Okay. You just need to find a good excuse for getting a better telescope and a different telescope. Awesome. All
New
right.
use case. Yeah.
Awesome. Well, I think we're through all the questions that the participants online they wrote in. So yeah, we're done. So thanks so much, Willie, and look forward
Thank you,
to the
Ward.
next session, which is actually a session where you will see us again. I think
Thank
that's
you,
the
Ward.
plan. Okay.
Cheers, everyone.
Cheers.
Bye.
Bye.